Today we learn discrete-time convolution, the fundamental operation that describes how LTI systems process signals. Given two discrete-time signals x of n and h of n, their convolution y of n is defined as the sum from k equals -infinity to infinity of x of k times h of n minus k. For finite-length signals, if x has m samples and h has n samples, the output y will have m plus n minus 1 samples. Let's see how to compute this with a concrete example. Method 1 is called shift and add. The idea is to express y of n as x of 0 times h of n plus x of 1 times h of n minus 1 plus x of 2 times h of n minus 2 and so on. Each term is a scaled shifted copy of h. You scale h by each input sample x of k, shift it to position k, and add all the copies together. This method directly follows from the convolution formula. Let's apply shift and add step by step. Our signals are x of n equals -1, 0, 1, 2, and h of n equals 1, 1, -1, 1. Starting with x of 0 equals -1, we scale h by -1 to get minus h of n, the values -1, -1, 1, -1 at positions 0 through 3. This first component is shown in red. Next, x of 1 equals 0. 0 times anything is 0, so this sample contributes nothing to the output. We skip it entirely. Now x of 2 equals 1. We shift h right by 2 positions to get h of n minus 2. 1, 1, -1, 1 at positions 2 through 5. This component is shown in green. Finally, x of 3 equals 2. We shift h right by 3 and scale by 2 to get 2h of n minus 3. 2, 2, -2, 2 at positions 3 through 6. This component is shown in purple. Now we add all components at each output index. At n equals 0, only the red contributes, -1. At n equals 1, -1. At n equals 2, we get 2. Continuing through n equals 6, the complete output is y of n equals -1, -1, 2, 2, 1, -1, 2, 7 values, exactly m plus n minus 1. Method 2 is called flip and slide, also known as the dot product method. First, flip h of k to get h of negative k. This reverses the signal around the origin. Then for each output index n, shift the flipped signal to get h of n minus k. Multiply x of k and h of n minus k element by element where they overlap and sum the products. This sum is the dot product of x and the shifted flipped h. Slide h one position at a time across x, computing the dot product at each step. Now let's verify using flip and slide. X of k stays fixed on the top row. -1 at k equals 0, 0 at 1, 1 at 2, and 2 at 3. For n equals 0, h of negative k sits at k equals 0, -1, -2, -3. Only k equals 0 overlaps. -1 times 1 gives y of 0 equals -1. For n equals 1, h slides right by 1. Positions k equals 0 and 1 overlap. -1 times 1 plus 0 times 1. Y of 1 equals -1. For n equals 2, 3 positions overlap. -1 times -1 is +1, 0 times 1 is 0, 1 times 1 is 1. Adding up, y of 2 equals 2. For n equals 3, all 4 positions overlap. The products are -1 times 1, 0 times -1, 1 times 1, and 2 times 1. The sum is -1 plus 0 plus 1 plus 2. Y of 3 equals 2. For n equals 4, x of 0 leaves the window. The remaining products are 0 times 1, 1 times -1, and 2 times 1. That's 0 minus 1 plus 2. Y of 4 equals 1. For n equals 5, only two positions overlap. 1 times 1 and 2 times -1. That's 1 minus 2. Y of 5 equals -1. For n equals 6, only k equals 3 overlaps. 2 times 1. Y of 6 equals 2. Same result as method 1. Y of n equals -1, -1, 2, 2, 1, -1, 2. Let's compare the two methods. Shift and add works signal by signal. Take each sample of x, create a scaled shifted copy of h, and add them all up. It's intuitive for understanding what convolution means physically. Flip and slide works sample by sample. For each output position n, compute one dot product. It's more systematic and often preferred for hand calculations. The key properties to remember. The output length is always m plus n minus 1, and the starting index of y equals the sum of the starting indices of x and h. Today we defined discrete time convolution. Y of n equals the sum of x of k times h of n minus k. We computed the same example two ways. Shift and add scales and shifts h for each input sample. Flip and slide flips h and computes dot products as it slides across x. Both yield the same result. The output has m plus n minus 1 samples. In the next lesson, we'll explore convolution properties like commutativity and distributivity and introduce continuous time convolution.